Cape Applied Math Exam, Unit 2, Paper 2, 2023. Let's jump into it. Question 1, Section A, Discrete Math. Let P represent the statement, it is 38 degrees Celsius today. And let Q represent the statement, it is Tuesday. Write each of the following in words. So this is not P and Q. So P, it is 38 degrees today. Not P, it is not 38 degrees Celsius today. And Q, what's Q? It is Tuesday. Not P imply Q, or it's a if-then statement. If not P, then Q. So if not P, if it is not 38 degrees Celsius today, then Q. Then it is Tuesday. This is a biconditional statement. If and only if. So P, if and only if Q. So if it is 38 degrees Celsius today, well, it is 38 degrees Celsius today. If and only if it is Tuesday. Given the following conditional statement, if I live in England, then I live in London. Determine each of the following. So it's a conditional statement. Live in England, let me refer to that as P. Then I live in London, let me put live in London as Q. Then the converse of that is Q imply P. We simply turn it around. So the converse would be if I live in London, then I live in England. So we simply reverse the statement. The inverse of P imply Q, the inverse of P imply Q is not P imply not Q. We simply negate the statement. So if I do not live in England, then I do not live in London. And the contrapositive, we simply negate the converse. So the contrapositive of P imply Q is not Q imply not P. So the converse would be, so the contrapositive would be just the inverse of the converse, which is if I do not live in London, then I do not live in England. Let's move on. Construct a truth table to determine if P implies Q implies not P and Q. So I want to check if the statement is a tautology. Now for it to be a tautology, all the truth values in the column here, final column here, must be true. So let's go ahead and construct this truth table now. So we have P, Q, so we have PQ. Since I don't have a ruler, let me try and draw a table as best as I possibly can. So we have PQ. We also need a not P. We need P imply Q. What else do we need? We need not P or Q. We need not P or Q. And then the final column is a statement. P imply Q imply not P or Q. So P or Q, P and Q, two statements. So we'll need 4 rows. Yeah, 4 rows. Alright, so the possible truth values of P and Q, both can be true. The first true, the other false, or vice versa, the first false, the other true, or both statements could be false. Not P is the opposite of P. So P, true, true, false, false. So not P would be false, false. True, true. P imply Q. The thing about the imply, the conditional statement, the only time we get false is for the true, false. So P imply Q. The true, false, we get a false there. All the other combinations would be true. Next, not P or Q. No, not P or Q. We're connecting the first and the third column using R. And the thing about the R table is always true except for the false, false. So R table, not P or Q. The second and the third column are combining, not P or Q. So not P or Q, we have a false here in the second row. So this will be false. Every other combination would be true. And then the final column, we're combining the fourth column and the fifth column as a conditional. And with the conditional, the only time we have false is in a true-false situation. Notice we don't have a true-false situation here. So all the combinations here would be true. And notice all the values are true. So hence the statement is a tautology. Part D of question 1. The following diagram shows two switching circuits, Y and Z. So Y, we have the circuit Y over here. We have a circuit Z over here. Derive the Boolean expression to represent the switching circuit for Y. So if we look at Y, notice, so we have P and Q for any power, for any electricity to go through. Both have to be closed. So this is P. This is P and Q. And this is P and R, and then R, so this electricity coming through can either go that direction or that direction. So the switching circuit would be P and Q, or it could the other direction where you have P and R. Another way to express it, and we use multiplication, so P and Q, that's PQ, or we use a plus sign, and P and R, that's PR. So either of these expressions would work. The switching circuit for Z, so notice in Z we have P, and if you go this direction, so you have P. If you go up, that's P and Q. And if we go down, other direction, well, so let's look at it again. So we can go to P, and of course, we can go either direction. We can go up, so we can go up to Q, or we can go down to R. So another way to write this expression is P times, bracket to represent that, Q plus R. So and multiplication, or we use a plus sign. So any of these two would work for Z, the same thing, and any of these two would work for Y. Part 2. Given that the switching circuit Y is logically equivalent to the switching circuit Z, and the cost of using one switch per hour is $6, determine the savings for a year, and a year is 365 days, of using switching circuit Z rather than using switching circuit Y. So if you compare switching circuit Z, let's look at them again. If you compare switching circuit Z to switching circuit Y, switching circuit Z has how many switches? Switching circuit Z, switching circuit Y has 1, 2, 3, 4 switches, and switching circuit Z has 1, 2, 3, 3 switches. So switching circuit Z has one less switch. So it would be more economical or cheaper to use switching circuit Z. Since switching circuit Z is simpler, has one less switch. So if I'm using switching circuit Z, the amount saved, the cost of one switch is $6. Alright, and the savings of a year is 365. So 365, so at the amount saved, okay, so calculate the savings, alright? So the yearly savings would be what you'll save on a switch, because switching circuit Z has one less switch, and the savings on one switch is $6. Alright, $6. $6 per hour. $6 per hour. So in a year has 365 days. So a year has how many hours? A year has 365, and a day has 24 hours. So a year has 365 times 24 hours. And then for each hour, you'll be saving $6. So the savings will be 365 times 24 times 6, and that gives us, so 365 times 24 times 6, that gives us 52,560. That will be the amount saved on one switch. Part E. The Boolean expression is given as R and P, or P and R, and Q and R or Q not imply, sorry, R not Q. Alright, so let's simplify the circuit. Let me write in a different form. So R and P, that's RP, right? R and P, that's RP. When they rewrite it, R, that's plus. P and R and Q. P and R and Q, that's PRQ. So this is P and R and Q. So that's PRQ. That's PRQ. And RQ. So and is times R plus Q, and close that, R, so that's plus, not Q. Let's simplify this statement. So what we could do is, let me just, I guess we could expand this bracket. So we have RP, expand, this will be PRQ times R, so that is PRQ times R plus X distribute to the Q, so this is PRQ times Q plus not Q. Alright, now we have RP, and here R times R is R. So one of the laws of Boolean algebra is that R times R, or A times A is A. So R times R is R. So this would be PQR. The same concept. Q times Q is also Q. So Q times Q, that's Q. Notice that's A times A. One of the laws of Boolean, A times A is A. So this is just PRQ. Since Q times Q is Q plus not Q. Alright, what else can we do? Now notice these are the same terms. So this is PRQ. We can factor RP. Let's factor RP. A common factor in all the terms here is RP. So we can factor RP. Since RP is in these first three terms, factor RP from the first term, we're left with 1. Plus factor RP from the second term, we're left with Q. And factor RP from the other term, we're left with Q again. Plus not Q. So we have RP times 1. Now 1 plus whatever. So this is 1 plus Q. Again, in the bracket, 1 plus whatever. Doesn't matter what that term is. 1 plus Q, whatever it is 1. So in Boolean, 1 plus 0 is 1. 1 plus 1 is also 1. So 1 plus whatever, it's 1. So the bracket will come to 1. Plus not Q. So RP times 1, that's RP plus not Q. So whichever method you use to simplify, then this should be it. If you want to rewrite it like this using the intersection and union symbols, this is also R and P, R and P, R to represent a plus sign, not Q, not Q. Alright, so either of these expressions will work. Next, we're asked to draw the corresponding circuit to represent the simplified Boolean expression in E1. Now, we weren't told whether we should do a switching circuit or a logic circuit. If we were to do a logic circuit, let me do both a logic circuit and a switching circuit. So a logic circuit, so RP, R times P, so we would have R and P going through an AND gate. And of course, we'll add that, and we'll add that to, so we'll have now not Q, forget not Q. So we need RP, so that's R and P. So we put those at the top. Or not Q. So coming through, we'd have RP or not Q. Let's move on to question 2. Joan wants to buy X oranges and Y peaches from the local market and sell them in her community to make a profit. Oranges cost 40 cents each and peaches cost 60 cents each. She only has $4.80, and so she cannot buy more than 5 peaches. An orange weighs 100 grams and a peach weighs 50 grams. Joan can carry no more than 0.8 kilogram of fruits home. So this seems to be a linear programming question. We're asked to determine the inequalities of the constraints that must be satisfied by the variables. So oranges, 40 cents. She only has $4.80 cash. So 0.4 times the oranges plus 0.6 times the amount of peaches. That's 0.6 times Y. And that should be less than or equal to 480, since she only has $4.80. So she can spend no more than that. She can spend less, but no more than $4.80. So that's one of our inequalities. That's our first inequality. Next, we are told that she cannot buy more than 5 peaches. So the amount of peaches represented by Y has to be less than or equal to 5. So the amount of peaches cannot be more than 5. And the final inequality, notice we have the weights in grams and the total amount is in kilograms. So we want to convert everything to the same unit. So to convert from grams to kilograms, we need to divide by 1,000. So 50 grams, 100 grams, we'll convert these to kilogram by dividing each of them by 1,000. So 100 divided by 1,000, that's 0.1, and 50 divided by 1,000, that's 0.05. 0.05 kilograms. And the orange, 0.1 kilograms. So we convert everything to be on the same unit just to be consistent throughout. So 0.1 times the number of oranges plus 0.05 times the number of peaches. And that should be less than or equal to 0.8. So we have our 3 inequalities. We need now to part 2. Can we simplify? I guess we can just leave as 4.8, not 4.80, $4.80. Alright, so can we simplify? I guess we can just leave these inequalities as they are. Alright, let's leave them as they are. Let's represent these graphs now, and let's represent these inequalities on graph. So on the grid provided on page 9, plot a graph to represent each of these inequalities. Using a scale, so there was an error with this paper. The 1 to 5 should be 1 to 1. Alright, so 1 centimeter to represent 1 unit on both axes. So let's just fix that. And we must shade all the feasible region that satisfies all the constraints on the graph plotted. So these are inequalities. Let's copy them to the graph sheet so we can look directly at them while we're doing our graph. So let's copy these. So these are inequalities. Let's do our graph. So the first graph, let's do the middle one first. Y less than or equal to 5. So the graph there will be y, the line y equal to 5. It's always important to label your graph. This is the graph of y equal to 5. Less than, of course, will be below, but we'll leave the shading until we have all 3 graphs. Let's do the top one next. Of course, it's a line. So we need to find out where the graph cut both the x-axis and the y-axis. So y-axis for peaches, x-axis oranges. So we need now to know where the graph cuts the x-axis and also the y-axis. So to get where the graph cut the x-axis, we can let the y be 0. So we have 0.4x equal to 4.8. And then to solve for x, we divide both sides by 0.4. So we get x is equal to 12. So the first line cuts the graph at 12 on the x-axis. Now we need to know where the graph cuts the y-axis. So this time now we're going to let the x be 0. So we're left with 0.6y equal 4.8. Divide both sides by 0.6. and we end up with y equal to 8. So this graph, we cut the y-axis at 8, x-axis at 12. So I connect these lines, and of course, always remember to label your graph. So this is a line 0.4x plus 0.6y equal to $4.80, $4.80, 4.8. And the final graph, the third one, 0.1x plus 0.05y, less than or equal to 0.8. So we need to know where the graph cuts the x-axis and the y-axis. So to know where the graph cuts the x-axis, replace the y with 0. So we're left with 0.1x equal 0.8. Divide both sides by 0.1. So x equal 0.8 over 0.1, which is equal to x equal to 8. So it cut the x-axis at 8. Next, to know where the graph cuts the y-axis, we equate the x to 0, and we'll be left with 0.05y equal 0.08. Divide both sides by 0.05. We end up with y is equal to 1.8 divided by 0.05. That's 16. So the graph cuts the y-axis at 16, the x-axis at 8. So we connect both points and we have our line. Always remember to label any line drawn. So this line represents 0.1x plus 0.05y equal to equal to 0.8. So let's just highlight our x and y axis there, which I didn't do. So less than, look for the critical region, the over area there. So that's area is for less than. Notice all the lines were less than. So that's the area that will fit, satisfy all the inequalities. We also need to make a note, take a note of all the critical points, all the endpoints. That's one endpoint there, that's 0.5. The other endpoint there, that's 8, 0. Another critical point there, that's 6, 4. All those areas are the corner points there of the critical area, shaded area. And the other one, it seems to be 4.5 for the x and positive 5 for the y. So these are all our what we call corner points or critical points. Let's just try and copy these now to the question paper. So these are our critical points from the graph. So Joanne expects to make a profit of 20 cents on the orange and 30 cents on each peach. Determine the maximum profit. So x for orange, remember y for peach. So the profit function is given as 0.2x plus 30 cents times the amount of oranges. Alright, so 0.3y. To get the maximum profit, now we need to try all of these values. And whichever value gives us the maximum value for the profit, P, then that's our maximum profit. So let's try them one at a time. So let's substitute 0, 5. And of course, substituting 0, 5, x is 0, y is 5. So we'll substitute these into the profit function. So it's 0.2 times 0 plus 0.3 times 5. And this works out to be 0 plus 0.3 times 5. That's $1.5, $1.50. Substitute 8, 0. Let's fix that better. So it's actually 8, 0. 8 for the x. So 0.2 times 8 plus 0.3 times 0. And this works out to be $1.60. Substitute 6 for x for 6, y for 4. So it's 0.2 times 6 plus 0.3 times 4. This works out to be 2.4. That's $2.40. I will substitute 4.5 for x and 5 for y. 0.2 times 4.5 plus 0.3 times 5. And this will also be, let's see, this will be $2.40. So the maximum profit is $2.40. And that's when Joan has 6 oranges and 4 peaches. Part B, determine the degree of E. So we have a graph there. So the graph E, the number of vertices, number of edges coming in or out E, and we have 4 of them. Identify 4 trails, starting with A. So what's a trail? A trail is simply a path. So we have to start at A. And we try to visit all the vertices without covering an edge twice. So a vertex is labeled by the alphabets there, the letters there, and the edge is a line that runs from a point to a point. So trail 1, let me do trail 1, or the first trail, we can go from A right around. A to B to C, then to F, then to E, and then to D. So notice we have visited, so we have visited all the vertices we have traveled all the vertices without covering an edge twice. Let's look for another trail. Let's use T2 to denote it. So again, we have to start at A. So we can go the other direction. A, we can go to D this time. Then to E. then to F, to C, and then to B. So again, we have covered all the vertices without having to cover an edge twice. Let's do a third trail. So we can start again. So we have to start at A. I want to travel all the vertices by taking a different path. So this time we can go A to E, then to F, then to C, then to B, then to A again. So it's okay. Again, it's okay to visit a vertex more than once. So notice we have visited A, we have traveled A more than once, but that's okay. What's important is that we don't travel edge twice. So it's okay to travel a edge, to travel a vertex twice, but we are not, since it's a trail, we cannot travel a edge twice, all right? So the vertex A, we can travel twice, or any other vertex we can travel twice, but we're not allowed to travel an edge more than one time. So F to C to B to A, and then to D. And we have another trail. So we need one more final trail. Again, we want to make sure we cover all the vertices without traveling an edge more than once. So A to E to D, back to A. That's a different path, right? To B, to C, and to F. So again, we have traveled all the vertices without traveling twice on an edge. So we have our trails, our 4 trails. Let's move on to part C. It seems to be a Hungarian algorithm assignment problem. A company decides to embark on a new project that consists of 4 tasks: research, advertising, sales, and auditing. The company selects 4 teams from among its employees, and each team submits an estimate in thousands of dollars for performing the 4 tasks. The company can only hire 1 team for each task to minimize the cost. And here we have our table, and we're asked to use Hungarian algorithm to determine how the team should be assigned in order to minimize the costs of the 4 activities. So we are using what we call Hungarian algorithm. So notice each of these values is in thousands of dollars. So team P, for example, that's 40 there, 40,000. They submit for sales. Team R, 220,000 for research, 170,000 for advertising, and so on. 70,000 for auditing. That's team R. So we need to find a way to assign the task to each team so that the cost is minimized. So we first need to do row reduction. So the first step in Hungarian algorithm, we're going to reduce each row, and we'll do that by identifying the smallest value in the row and subtracting that value from every other value in the row. So let's create a little table here to do our row reduction. So we need 4 rows. Since it's a 4 by 4 matrix there, we need to ensure we have 4 rows and 4 columns. So in row 1, the largest value there is, well, the smallest value in row 1 is 40. So we need to subtract 40 from every other value in row 1. Alright, let's begin. So 200 minus 40, that's 160. 150 minus 40, that's 110. 40 minus 40, that's 0. And 80 minus 40, that's 40. Next, row 2. Smallest value in row 2 is 25. So we're going to subtract 25 from every value in row 2. So 180 minus 25, that's 155. 160 minus 25, that's 135. 25 minus 25, that's 0. And 100 minus 25, that's 75. Now we move on to row 3. The smallest value in row 3 is 30. So we're now going to subtract 30 from every other value in row 3. So 220 minus 30, that's 190. 170 minus 30, that's 140. 30 minus 30, that's 0. And 70 minus 30, that's 40. The final row, the smallest value in the row 4, that's 20. So it's going to subtract 20 from every other value in row 4. So 120 minus 20, that's 170. 140 minus 20, that's 120. 20 minus 20, that's 0. And 90 minus 20, that's 70. Alright, so that's a row reduction. So now we're going to do our column reduction. Just create another 4x4 table. And for the column reduction, we do something similar, but this time we're going to look for the smallest value in each row and subtract that value from, smallest value in each column and subtract that value from all the values in the column. So yes, we have 4 rows and 4 columns. So in row 1, the smallest value there is, column 1, keep saying row. In column 1, the smallest value now is the smallest value in column 1 is 155. So we're going to subtract 155 from every value in the column. So the first one, 160 minus 155, that's 5. 155 minus itself, that's 0. 190 minus 155, that's 35. 170 minus 155, that's 15. Column 2, smallest value there is 110. So we're going to subtract 110 from every value in column 2. So 110 minus itself, that's 0. 135 minus 110, that's 25. And 140 minus 110, that's 30. And 120 minus 110, that's 10. Now to the third column, smallest value is 0. Subtract 0 from 0. We're left with 0 in all cases. The final column, the smallest value there is 40. So we're going to subtract 40 from every value in column 4. So 40 minus 40, 0. 75 minus 40, that's 35. 40 minus itself, 0. And 70 minus 40, that's 30. So let's cover all the zeros. So we draw a line through all the zeros in each, right? And we end up with 4 lines. So we have an optimal situation here. The number of lines it took to cover all the zeros is 4, which is equal to the number of rows, or the order of the matrix. It's a 4 by 4 matrix. It took 4 lines, so we have an optimal situation. Now we need to make the assignment. Notice in the final row, we have only 1 0. So we can only assign that 0. Notice the third 0 in the row. So we can only assign that 0 to team S. The third value there in the bottom row assigned to team S. So sales will be assigned to team S. So we're trying to get the minimum cost by assigning the teams with the correct thing. Now if that 0 is used, then for the third row, we'll have to assign that 0 to team R. That's a label PQR. So that 0. So we can't assign the 0 above TS. So that 0 there in the final 0 there in column 3, we assign 70,000. So we assign auditing to team R. So we have to assign research and advertising now. So the only option we have here now is to assign advertising to team P. On the other 0, we assign research to team Q. So notice how we began. We started with the row that has only 1 0, which was for team S being assigned to sales. And then we do the other assignments. And that's our optimal situation. So for the cheapest cost to the company, team Q will do the research, team P will do advertising, team S sales, team R auditing. So to get the minimum cost, we add all of these values. So team P will do advertising, team Q research, so 150 plus 180. That's 150 plus 180, that's 330. Plus 70, that's 400, plus 20, that's 420. And remember the figures represent thousands of dollars. So 420 would be represented by 420,000, since each figure are really thousands. So that's it. Let's move now to question 3.